Good morning, everyone. Welcome to today's presentation. I am Dr. S.K. Singh, and I am excited to share with you insights on thin layer chromatography, or TLC. Today, we'll explore the fundamentals of TLC, its applications, and how it plays a vital role in analytical chemistry. So, let's dive into this fascinating topic together and see what makes TLC such a powerful tool in laboratories worldwide. Today, I want to introduce you to thin layer chromatography, or TLC for short. It's a technique that's known for being simple, quick, and cost-effective, making it very accessible for many laboratories. TLC is primarily used for three key purposes: separation of compounds, identification of those compounds, and checking their purity. These functions are crucial in various fields, especially in pharmaceutical industries where precision and reliability are vital. In the context of our overall discussion, TLC plays a significant role because it allows us to analyze mixtures efficiently and accurately without the need for complex equipment. The way TLC works is based on the principle of differential adsorption and partitioning. Essentially, we have a stationary phase, usually silica gel or alumina coated on a plate, and a mobile phase, which is a solvent system. When a sample is applied, the different compounds in it interact differently with these phases, resulting in their separation as the solvent moves up the plate. This simple yet powerful concept makes TLC a valuable tool across many applications, from drug standardization to active pharmaceutical ingredient analysis. Let's talk about the principle of TLC, or thin layer chromatography. When you apply a sample onto the TLC plate and place it in a solvent chamber, the mobile phase starts to rise through capillary action. This movement is what separates the components of your sample. Now, these components don't all travel at the same speed. Their rates depend on a few key factors. First, polarity plays a big role. More polar compounds tend to interact differently with the stationary phase compared to nonpolar ones. Second, solubility in the solvent can influence how far they travel. And third, how they interact with the stationary phase itself affects their movement. Now, to quantify this separation, we use the RF value, or retention factor. This is a characteristic number that helps us identify compounds. It's calculated by dividing the distance a compound moves by the distance the solvent front moves. So, in simple terms, the RF value tells us how far a particular substance travels relative to the solvent. This is crucial because it allows us to compare results across different experiments and identify unknown compounds based on their RF. Overall, understanding these principles helps us interpret TLC results accurately and makes this an essential technique in analytical chemistry. Let's walk through the general procedure for thin layer chromatography, or TLC. First, you need to prepare your TLC plate, making sure it's clean and ready for spotting. Next, you'll spot your sample onto the plate using a capillary tube, being careful to apply a small, concentrated amount. Then, place the plate into the developing chamber, which contains your mobile phase solvent. It's important to ensure the solvent level is below the spot line to prevent contamination. Allow the solvent to rise up the plate by capillary action until it reaches near the top. Then carefully remove the plate and mark the solvent front immediately. After that, you'll visualize the spots. This can be done using UV light if your compounds fluoresce or by applying specific reagents that react with your analytes. Once you see the spots, you'll measure the distance each spot traveled relative to the solvent front, which allows you to calculate the RF values. These values help identify or compare compounds in your sample. Now let's touch on the materials and components involved. The stationary phase is typically silica gel, which is the most common, but alumina can also be used depending on your analyte. The mobile phase consists of organic solvents like hexane, ethyl acetate, or methanol. These are chosen based on the polarity of your compounds. Your sample might be a drug, an extract, or an intermediate compound you're analyzing. Detection methods are key in visualizing your spots. UV light at 254 or 366 nanometers can reveal certain compounds. Alternatively, You can use iodine chambers or spray reagents like ninhydrin or Dragendorf's reagent, which react with specific molecules to make them visible. All these components work together to give you a clear picture of your sample's composition and help in qualitative analysis. Let's take a closer look at an example of paracetamol analysis. First, we used a solvent mixture of ethyl acetate and methanol in a 9:1 ratio. This helps us separate the components effectively during chromatography. When comparing the standard and the sample, if they have the same RF value, that confirms the identity of paracetamol in the sample. However, if we observe extra spots on the chromatogram, that indicates the presence of impurities, which is important for quality control. This process is essential for drug identification, ensuring we're analyzing the correct compound. It's also crucial for purity testing, confirming that the sample is free from contaminants. Additionally, stability studies rely on these techniques to see how the drug holds up over time under different conditions. Impurity detection is a key part of maintaining safety and efficacy in pharmaceuticals. And all these applications, drug identification, purity testing, stability studies, impurity detection, highlight how vital chromatography is in the pharmaceutical industry. It helps us ensure that medicines are safe, effective, and of high quality. Let's take a closer look at this herbal example, specifically turmeric extract. As you can see, it contains multiple spots, or curcuminoids, which are the key active compounds responsible for its health benefits. These compounds can be identified through a unique TLC fingerprint, which essentially acts as a chemical signature for the extract. Now, when we analyze an adulterated sample, we notice a different pattern in this fingerprint, indicating that something has been added or altered. This is where fingerprint profiling becomes so valuable. It allows us to detect any adulteration by comparing the fingerprint patterns. Additionally, it helps us identify specific marker compounds that are characteristic of genuine turmeric extract. This approach has significant applications in the herbal industry, ensuring product authenticity and quality. Overall, fingerprint profiling is a powerful tool for safeguarding herbal products and maintaining consumer trust. Let's take a closer look at this API example for synthesis monitoring. When the start material spot disappears, it indicates that the reaction has begun and the initial reactants are transforming. Soon after, you'll see the product spot appear, which confirms that the reaction is progressing as expected. This visual change is a clear sign that the reaction has reached a certain stage, specifically, that it's complete. This kind of reaction monitoring is crucial because it allows us to keep track of the process in real time without needing to stop and analyze samples repeatedly. It also helps in identifying intermediates, those transient species that appear during the reaction, and ensures we maintain precise control over the process. In the broader API industry, these capabilities are vital. They enable us to optimize reaction times, improve yields, and ensure consistent product quality. So, this example shows how powerful in situ monitoring can be for maintaining control and efficiency throughout pharmaceutical manufacturing processes. Let's take a look at some of the limitations of this method. First, it is less accurate than HPLC, which means there can be more variability in the results. This can be a concern when precise quantification is required. Speaking of quantification, it's also limited in its ability to be used quantitatively, so it's not ideal for exact measurements. Another point to consider is that the results can depend heavily on the operator's skill, making consistency a challenge. Additionally, it offers lower resolution compared to more advanced techniques, which can affect the detail and clarity of the analysis. Now, while these limitations are important, it's also helpful to understand the advantages of this method. It's low cost, making it accessible for many labs. It allows for fast analysis, so you can get results quickly. The operation is simple, which means it doesn't require extensive training. Plus, it can handle multiple samples at once, increasing efficiency and throughput. So, when choosing a technique, it's all about balancing these pros and cons based on your specific needs. Let's wrap things up with a quick look at the conclusion. As we've seen, TLC, or thin layer chromatography, is still quite widely used across a variety of industries. It plays a crucial role in the pharmaceutical sector, helping with the analysis of complex compounds. The herbal industry also relies on TLC to identify and authenticate natural products. Additionally, the API industries use TLC for quality control and purity testing of active pharmaceutical ingredients. It's important to remember that TLC remains essential for quick screening processes, especially when rapid results are needed. Despite the advent of more advanced techniques, TLC still holds a significant place because of its simplicity, cost-effectiveness, and reliability. So, even in today's high-tech analytical environment, TLC continues to be a valuable tool for ensuring quality and safety in many fields. For further support, please don't hesitate to reach out. We're here to help you with any questions or additional information you might need. Just contact us through the details provided, and we'll be happy to assist. Thank you so much for your time and attention today. I truly appreciate it. Remember, we're committed to supporting your success beyond this presentation, so feel free to get in touch whenever you need. Thanks again, and have a great day.